Okay, let's talk a little bit about ionic nomenclature. Now, naming compounds or nomenclature is just a fancy way of saying that. You have nomenclature in any discipline. It's the terminology used so that everybody knows what you're talking about. It is divided into organic compounds, those containing carbon. We'll save those for another day. And inorganic compounds, which is the rest of the periodic table. We'll focus primarily on inorganic compounds for the purposes of this course. There's a few common ones that we'll kind of put in at some point. So an ionic compound, the naming is done by naming the cation first and then the anion. Cations are formed from a metal, have the same name as the metal. For example, Na plus is the sodium ion. If the metal can form more than one cation, then the charge is indicated in parentheses next to the name. Alternatively, OUS or IC endings can be used to indicate the higher charge. Examples of that would be Cu plus is copper 1, Cu2 plus is copper 2. And notice it's just a Roman numeral with the charge. If it's a polyatomic ion formed from nonmetals, then it gets IUM. The one that's important for ionic nomenclature is the ammonium ion, NH4 plus 1, not to be confused with ammonia, NH3. Okay, as we mentioned before, these are the positive ions you are required to know. Notice the group 1A ions are all plus 1, including hydrogen, even though it's not technically a metal. Group 2A ions are plus 2. Group 3A ions are plus 3, as we mentioned. There's some transition metal ions that don't get a Roman numeral with the OUS or IC ending that are common. Those are zinc and silver. You don't want to put a Roman numeral with those. Other cations. Remember, we mentioned the OUS and the IC endings, and you can see them there as well. Like you got cuprous and cupric there instead of copper 1 and copper 2. You got plumbous and plumbic. You got ferrous and ferric. And those are all ones you need to know. And stannous and stannic. You could do mercurous and mercuric as well. It's always the lower and the higher charge. Notice the mercurous ion has an odd formula. And it's Hg2 2 plus. And the ammonium ion is the only positive polyatomic ion where that really works. Okay, let's talk a little bit about anions now that we've talked about cations. Monoatomic anions, that is with only one atom, are called ide. They get an ide ending. For example, chlorine becomes chloride. Fluorine becomes fluoride. Oxygen becomes oxide, so on and so forth. There are a few polyatomics that are common that have ide as well. Hydroxide, OH minus, cyanide, CN minus, peroxide, O2, 2 minus, all of those have ide endings even though they're polyatomic. Polyatomic ions generally containing oxygen other than those get an ATE or an ITE ending. The ones with the more oxygen get ATE. For example, NO3 minus 1 is nitrate, NO2 minus 1 is nitrite. Notice they differ by 1 and only 1 oxygen. Now, you may not have all the members of the series. You may only have one member of the series that actually exists. But here's how they would go. If you had more than 2 in the series and you had one more oxygen in the 8, you would have a per prefix in the AT ending. Then if you subtract 1 oxygen, you get 8. Subtract another oxygen, you get ite. And then lastly, if you subtract even one more, then the ite, you add a hypo prefix and ITE ending. What you'll notice is that they have the same element at the beginning different numbers of oxygens and then the same charge. Here are some examples. You can see chloride, but then if you add an oxygen, you get hypochlorite. Then you get ClO2 minus 1 is chlorite. ClO3 minus 1 is chlorate. ClO4 minus 1 is perchlorate. And you'll want to know the iodine and bromine variations of that same series as indicated in this table. Make sure you know those. If you need to pause this video and copy that down or something, that would be certainly be fine. But it works the same way for iodine and bromine variations of that series. Now, if you have hydrogen in your anion, you can just add the word hydrogen or bi in the case of some anions. Usually you add bi if the anion starts with has a -2 charge. You don't if it has a -3 charge. You can add dihydrogen for 2 hydrogens, etc. If you add enough hydrogens to totally cancel out the charge, then you have an acid. And we'll talk about that one. We'll mention it briefly here, but then mention it more when we talk about acid nomenclature in a slightly later presentation. So let's look at some examples here. These are adding hydrogens to anions, and we'll go through how to name each anion and then what happens when we get to the neutral acid. Okay, let's work out these hydrogen containing ions. So here's the one with no hydrogen in part A, and it's called carbonate. Now if we add a hydrogen to it, we can add the word hydrogen, call it hydrogen carbonate. Alternately, we can call that bicarbonate. But if we add enough hydrogens to neutralize it, that's going to be named as an acid because it's not an anion anymore. There's no negative charge. In this case, this one's called carbonic acid. We'll talk about acid nomenclature in an upcoming video. PO4 3 minus is phosphate. And so if we add a hydrogen, it's going to be hydrogen phosphate. Add 2 hydrogens, we're going to say dihydrogen phosphate. And remember, I didn't say bi for this one because you don't usually do that if you start with a -3 charged ion. If we cancel out all the charge, again, it's an acid, and this one happens to be called phosphoric acid. The negative ions are again largely due to which column on the periodic table you're on. And notice hydrogen's +1, but it can also be -1. Even on some old periodic charts, you'll see it written above group 7, indicating it can take on that -1 charge. You can see all your halogens, fluoride, chloride, bromide, iodide, all -1. Oxides -2, along with sulfide. And then you got nitride, peroxide. And then you got your polyatomics, the N and ATE or ITE. The one to make mention of, acetate is actually an organic ion. Organics only get 8. And so that one's common, so acetate. You can see our friends carbonate and bicarbonate there. Sulfate and sulfite, bisulfate, bisulfite. Chromate and dichromate are worth mentioning because of the It's not two chromates. It has a different formula, Cr2O7 2-, as opposed to chromate CrO4 2-. There's a couple of common compounds down there, ammonia gas, hydrogen peroxide, water, and propane. I would also remember those formulas for the test as well. And that will give you a list of more common compounds as they come up. Okay, so let's look at some ionic nomenclature. We got two names that are going to go to formulas and two formulas that are going to go to names here. And so we're going to work through each one of those and determine the nomenclature of them or the formula of them. Hydrated salts. Some ionic compounds will come in a certain number of waters of hydration. The number of waters of hydration are indicated with the Greek prefix. And we'll mention those a little bit when we talk about the binary molecular compounds. I'll have a list of those. Otherwise, the ionic compounds named normally, MgSO4.7H2O is magnesium sulfate heptahydrate. CuSO4.5H2O is cupric sulfate pentahydrate. Heating the salt will liberate the waters of hydration, and they'll go off in the gas phase. Sometimes that is accompanied with a color change of the salt. In our case, the copper salt, when you heat it, becomes white when heated, and so you see a nice color change there. So the hydrated salt is blue and the anhydrous salt's white, which helps you notice the difference in the two salts. Here you see a picture of the blue copper sulfate, this cupric sulfate on the left, and the anhydrous cupric sulfate on the right. And you can see the color change between the two salts. Okay, so let's look at this ionic nomenclature. If we take calcium and chloride, we know calcium is in group 2A, and so we can write Ca2+. Chloride is in group 7A, so we're going to write Cl-. You may not have to keep writing these ions for every problem, but it helps when you're just starting out. So what formula am I going to make from that? If I do my crisscross thing, we talked about the ionic formulas part, it's going to be CaCl2 as the proper formula. If we do aluminum nitrite, it's going to be Al3 plus NO2 minus. And so we do the same thing. So it's going to be Al, then in parentheses, NO2, then outside of the parentheses 3, because I've got to crisscross that 3 over here, and then 1 goes over there. Notice I didn't do anything to the subscript on the subscript in the polyatomic ion. Now, if we want to take it the opposite way, we have to infer what the charge on that copper is. So if we got a copper and we don't know its charge, but perchlorate is a polyatomic ion, and I could get its charge off the list. So we know it's ClO4 with a -1 charge. Since there's 2 of those, we have to infer that copper has to be a 2+ to balance it out. 1 plus 2 copper is going to even out 2 minus 1 perchlorate ions. And so what we're going to do is we're going to call that copper 2 perchlorate. Alternately, instead of copper 2, we could have said cupric perchlorate. Last but certainly not least, we got 2 polyatomic ions put together. So all we really have to do is name the polyatomic ions. NH4 is ammonium, so it's ammonium. SO4 is sulfate, so we're going to call that ammonium sulfate. And that would be the formula for that compound.